Welcome, everybody. This is the fourth day of the EA Global Summit 2020, the virtual conference connecting the entire EA practitioners throughout the globe. I'm Rashid from the EA Global Summit team. It is a pleasure to have Richard, a technical consultant and developer for the EA architect, who will be presenting on the topic Embedded Engineer. It would be nice for any queries if you can use the Teams channel shared in your chat window so that Richard will be able to look into it post the session. And Richard, do you want to take over?
Yes, of course. Thank you.
Yeah, thank you.
So welcome. My name is Richard Deininger, or Ritzo for short. I'm lead application developer for the embedded engineer and technical consultant for enterprise architect at Liebe. I'm specialized in code generation and behavioral modeling, especially for state machines. We at Liebe have more than 10 years experience with behavioral code generation. And since 5 years, we are using this experience and the feedback from our customers to develop and improve the embedded engineer. Today, I will show you how to generate MISRA compliant code from UML models. And if you have any questions during this presentation, please send them to us via the chat. And at the end of the presentation, we have a short Q&A, and I'll be also available at the MS Teams chat. So every time I present the embedded engineer, I get these main questions. Let's go through them. So why should I start generating H files, or why should I start with generating H files? Starting with something new is always hard. So we do it step by step, and starting with a well-defined interface is always a good idea. You can even leverage existing legacy code or libraries to help you along the way. What are the advantages of code generation? The accuracy of the code increases since Embedded Engineer will generate consistent MISRA compliant code and styling. Also, the model will be in sync with the code. As everybody knows, model and code tend to drift apart over time, and EA is mostly used for documenting legacy code. This will change. Do I have to model everything? The key word here is abstraction. Use existing libraries or your legacy code. Implement behavior step by step and where it makes sense. This, of course, may differ from user to user. How can I improve the traceability? Currently, traceability always ends up inside the model and is usually only shown via a relationship matrix or a table of some sorts. With code generation, we can forward this information into the code. And of course, can I modify the code? And how about round-trip engineering? Those 2 points are usually connected. Real round-trip engineering was one of the hardest things you can do with UML and code. But with Embedded Engineer, we think we found a way that make architects and developers happy. I'll show you as we go along. So how do we trace requirements currently? As previously stated, tracing requirements is usually done with tables, or in the case of Enterprise Architect, with the model and with the relationship diagram, which is basically also a table. If we want to have requirements also annotated inside our code, we usually depend on the software engineer doing this for us. And this is always a hassle. Of course, with Embedded Engineer, we can bridge this gap. After importing your requirements from your issue tracking or ALF tool, or even create them directly in the Enterprise Architect, the Embedded Engineer can create comments inside the code establishing a link back from the model to your requirements. And with this first steps, we already start with a short demo on how this is done. In the upcoming demo, I will show you the first steps with Embedded Engineer, what you need to do to generate code from an UML model and how easy it is. I'll show you reverse engineering, first steps of it, how you can import libraries or already available legacy code to you to use inside your model, and how it will help you by your step-by-step approach. And also, of course, customized documentation and code styles, how you can customize the code to fit your company's coding guidelines. And with this, let's switch over to the Enterprise Architect. Just give me a second. I've already prefabricated a small model here. And with this model, you see we have some requirements. Starting with the requirements, of course. We want to create a button reading functionality where you can read a button from some target device. Of course, we want to have a target independent implementation for this. You see here we have a provided target specific implementation for our interface, which I previously generated. We want to have, during button reading, we have a debounce buttons, so we don't have any jitter in our code, in our signal. And of course, we want to support long button presses. We want to use signals to propagate these button presses throughout the code or throughout our application. And for this, we also need to implement some kind of send signal action. Let's just simply start by looking at the code, what we have here. We have our interface, our read button pin, our read pin, or pin reader, with our initialization and our read functionality already in there. So we have an interface which we can use over multiple applications or multiple components. In this case, we want to provide a target-specific implementation for the button reader and, of course, the reading functionality. For this, we simply add a class, and in our case, we want to have an Arduino pin reader, typo, our class here. And now we simply drag drop on the upper right corner, we simply drag drop the arrow onto our interface and say we want to realize this interface. And of course, we want to realize all the selected operations. And with this easy step, we have already an implementation or a first-hand implementation for our interface. To now use this and get code out of this, we simply need to switch to our package where we generated it. The name of the package is up to you. And we simply go to stereotypes and use the Liber Embedded Engineer profile, which you get when you install Embedded Engineer. And there we use the LL Embedded stereotype down here. When clicking on OK, we see we have the LL Embedded stereotype here. With this LL Embedded stereotype, we also get some tagged values shown down here. First, we have the generation language, which we can choose. In this case, for embedded devices, of course, C and C++. And we have a generation directory. Where do we want to generate the source to? In my case, I want to have it right beside my model. So I can use relative paths like generated. And if I want to, I can even use the selector and go down here and select a hard-coded path if I want to, CTMP or whatever. Or again, a relative path. This relative path is always starting from the EEP file. So meaning the directory where your EEP file is located and then the relative path you entered here. Embedded Engineer also allows you to use the local paths already stored in Enterprise Architect simply by using the known annotation of EA by %, then your path name and %. And of course, you can also mix this up with relative paths. So you can use the local path and then add a relative path or an extended path to it. It will also work. Should this path be not available, you get prompted by an embedded engineer that there is something missing and you need to either generate it or let embedded engineer generate it for you. So easy, step by step, select the package, give it the embedded stereotype, select the generation language, select the generation directory, and put some classes or interfaces in there simply with some functions. And then all you need to do is right click on the package, specialize, Embedded Engineer 3.0, and generate code. The generate code progress dialog will pop up and you will see what is happening. Currently, we have created 3 files, of course, into our path here. And they can now right click on Embedded Engineer and open generation folder. And with this open generation folder, we get our folder right here with our 3 files in here. We also have a UDI file, a UML debugger information file, which can be used with our UML debugger, where you can debug the code on the target using your UML model. It's also included within Embedded Engineer. You see the relative path up here, shows goes right away from the EAP Summit EAP file to our directory. Now let's see what we have in here. Let's just open the code. We see our pin reader H file, our interface, with a simple definition of our 2 operations. We have our Arduino pin reader in here with our include of the pin reader. So we have our declarations for our operations. And we have our C file containing the 2 implementations from the interface, the reader, and the initialization. I told you that we want to have tracing to our requirements. This can be easily done. So we want to have a implementation for our pin reader interface. This was done realized with this class. So we use a realize connector. Again, drag dropping the connector down, realization. And we may even say that we have fulfilled the create a button reading functionality with this read operation down here. Again, drag dropping. In this case, we're using a trace. And we can, on the left-hand side of the connector, click on it, go to link to element feature, go to operation, and say we want to have this operation linked to it. So now we have these 2 requirements linked to our code. And to get the information out to the code, we simply generate the code again. And we will see that in our C file, we have there the provide target implementation for pin reader with our GUID linking back to the requirement itself, and the create button reading functionality, again with the GUID linking back to our element. And since we flagged the operation itself, we have an implementation for our button reading functionality and an end of the implementation for our button reading functionality inside the operation. So now we have code generated and we have our requirements linked to it. I also said that we can use reverse engineering and use legacy code or library code already available to us. So let's do this simply by going to external, because we don't need this code to generate it because it's already on our system. Simply use an external package, go to development, files, in this case C file, and we use the already existing reverse engineering functionality of Enterprise Architect to import our Arduino H file. In this case, this gets imported as a class. We want to have this as an interface, a simple change of type in here, so we can use it. And now that we have this interface in here, we can use it with our button reader. simply by adding it to our diagram and using a connector, in this case a usage connector, since we use this interface. We don't realize it, we just use it. And this usage will get translated by the embedded engineer into an include. And now we can add code to the read functionality. To do this, we could use the integrated code editor of Enterprise Architect. But Embedded Engineer, with the new version 3.0, we have added a new feature called the code editor itself, the code editor. And when we open it, we can simply click on the read functionality. You see here, when I open it on a package, we don't have any code inside the package, so there is no code edition supported. But as soon as I click on the read functionality, we see we have an operation called read, and we may enter code in here. We added this functionality to the Embedded Engineer because with this code editor, we allow the user to not only have syntax highlighting and support for tab indent and stuff like that, but we also support auto-completion and IntelliSense over the whole model. So you can add model elements in here, and you can add model attributes and operations pretty easily. In our case, we will use the digital read from the Arduino code. So let's just input here digital read, and then of course, since we have a pin here with the pin ID, and since this is opaque code, this is handwritten user code, we also need to add the semicolon at the end. We save the whole thing, and when we now generate the code again, we'll see that we have added this functionality to our code. Let's go over here. We see digital read pin in here. So pretty easy to use an existing library. And of course, I forgot, on the other side, we have the include to the Arduino H, so we can use this function, to call this function. Now that we have a pretty simple implementation, a pretty step-by-step approach to it, we want to have our custom documentation. As I said, you can customize the code to suit your company's guidelines, the coding guidelines. And for this, simply go back. And the most interesting thing is comments. We have a simple comment here for function. This is just the operation of the interface, and we have a simple file header here. And we can update this simply by going again on the package, on any package level you like. We add a custom documentation tagged value. And with this custom documentation tagged value, we'll get again new headers up here, new tagged values up here, called the field header, the file header, and the method header. So for every field, for every file and every method, we can add a new header and use a template-driven engine to generate our comment for us. For this, we have a good example at our help site. So we'll just use this one here in additional features, custom documentation. We'll see down here the basic example implementation of the current file header. So we won't change that much. Let's just go over to EA, input this here, and to show you that we can change this up here any way we like, we just put EA Summit 2020. Of course, you see in this round bracket, we have model path, model element, and so on. As I said, this is template driven, and the help aids you here with the information of what kind of elements you can use. Then we go to the method header. In this case, this will be a little bit more obvious. Here we have name, return type, and parameter. Contrary to before, where we just had, this is an implementation of operation A, B, and C. So now that we have a custom header and custom file header, we also want to change the coding style, as I said previously, simply by opening Embedded Engineer again, and we have the model settings. Model settings are again stored on package level, so you can change this throughout the packages as you like. Here we have the code editor save strategy. So in this card is discard changes, where we used our code editor, so we actively need to click save. Do you want to generate signals and so on? So there are many issues in many items in here, and we have a Clang format style options, where we can enter our Clang format options. And in this case, we just say the intent. We change the intent of an operation from 2 spaces to 4 spaces to 2 spaces, and simply save it. And when we now regenerate the whole thing, generate code, we will see that we have now the new information available to us. We see here, before I update it, you see here on line 27 that we have 4 spaces in here, and we have our simple operation header and our simple file header. And as soon as I reload the file, we have our customized file header, and we have our customized operation header. And of course, we have, in this case, 2 indents, 2 spaces indent in here, where we can change anything up we like. Okay, so much for our first steps with Embedded Engineer. But only using implementation of interfaces, your legacy code and requirements wouldn't be all. We want to generate code from behavioral models. So why should we do it? Or to be more specific, what advantages gives it? As architects and developers, we're facing more and more challenges and need a way to handle them. As you see in this list, functional safety, complexity, traceability, and documentation. These are issues that demand clear structures, ease of readability, ease of knowledge transfer throughout the developers, and reliable code. And we think that code generation does achieve exactly this. And to show you how it is done, how to generate code from behavioral models, we have the next demo. And in this, we'll show you how to create code from behavior, of course. We will create some activity diagrams, state machines, and I will show you the resulting code. We will talk about abstraction, or where do I need to stop modeling, or how far do I go down this rabbit hole. But in contrary to Neo in the matrix, we have more options than just do or don't. We can choose what we want to do. And of course, at last, what is this SMF? You will see along the code when you generate it, everywhere is this SMF structure, and why do we need it? So back to the A. Since this is a pretty big topic, I've already have some prefabricated code up here. We'll just simply drag drop it down into our source directory and so source package, and simply add the button implementation down here. So as our requirements already shown us, we want to create a button reading functionality. For this, we want to have the implementation of our Arduino pin reader. And since we want to use this, again, we use our usage connector to get our including. Then we have some other requirements. For example, we want to debounce the button pin. For this is our debounce variable. And to debounce this, of course, we want to have a last change time when it was last updated. We need to define our button pin. So these are basically some basic attributes in there. And we want to save the current or the last button state, so the state that we're currently in. To do all this, we have some functionality in here. We have already some some activities and some state machine. And to add a new behavior, we simply go on the class, right click in the browser and say add activity with diagram. And since we have a send button press, so our signal which we want to send, and we also want to support long button press, we create a send long pressed activity. In this case, we are modeling the send long button pressed activity. We use an initial activity, of course, and then we use an action, simple action in here. By control clicking, I can select specific actions. In this case, I want to have a send signal action because we want to send a signal out that the button was pressed long. We give it a control flow, so we know that we start here and then we go to the send signal action. And since we want to send a signal, we simply go to conditions and select the signal which we would like to send. And this would be the button pressed long, and we'll save the whole thing. What will happen is that the embedded engineer will create from this activity an operation, and within this operation it will create a specified function call called send signal action, which need to be implemented on the user side, but later more. We also have other activities. The send pressed will be the same as the long pressed, but we have also the button read, and here comes the point abstraction into mind. So this is a pretty low abstraction example. So we have low level of abstraction in here. We have defined everything inside our model. So let's go through it. We start, we have a read variable action. We read the button pin, and the result from this read will send to the input pin, to the parameter of this call operation action. This call operation action is, of course, our read pin interface, which we implemented for the Arduino pin reader. And the result, so the result of this call then gets forwarded to the value of a write variable action, where we simply write a new variable called integer current state. So pretty many actions just for a simple read-write transition. You will see later on, transaction. Then we have a decision where we check, has the current state changed from the last state? So do we have any change in here? And if we have any change in here, is the debounce time run out? So do we need to check this, or is this again inside the debounce timing? Should this be the case? So should we change this? Then we again read the current state and pass the result via an object flow down to a write variable action. Again, the question, this is pretty hardcore. Why do I need to do this? Why can't I have a higher abstraction level? As I said, it's up to the user to choose the abstraction level he likes. In this case, it's very low to show you what an embedded engineer is capable of. But if you read along, you know that we are missing something. We're missing the last changed state, simply because we need to have it updated after any read to have a valid debounce. So to do this, we'll use a little more high abstraction approach to it. We simply add an action and we say, okay, store last state change time. So this is basically what we want to do. We want to use a control flow down here, and this would be the next section. Since we used a normal action, an opaque action, opaque meaning we don't know what this action does for us, in contrary to our read variable action, which is well defined, just reading variables, or call behavior, just calling a behavior or calling an operation in this case. Here we have opaque action where we don't know what is happening here. And when I click on it, you see we have on our code editor, embedded engineer code editor, we have the ability to change the code in here. So we go in here and say, instead of redefining this whole stuff, we make a little higher abstraction level implementation. And here you will see the auto completion, just the me pointer, where we use it, you will see shortly. And then I press dot, and as soon as I press dot, you see we have an update from our attributes down here. So all the attributes inside the model get updated in here. So we want to have the last change. And then, of course, since we're using Arduino, we want to have millis because we want to have the last milliseconds in here and save it. So as soon as we have done this, we know that we have finished the debounce here. So we can add, if we want to, a trace to the whole thing. And of course, again, we generate the code for it. And we'll take a look. Oh, I'll skipped one step ahead. We'll need to update the state machine first. So before we do this, before we look at the code, let's look at the state machine. So we created an activity. We updated an activity. So I showed you how to use behavioral code with functions. And now I'll show you how to do it with state machines. We'll simply go inside our state machine. Again, I have some prefabricated stuff in here where we have a do action. In this do action, this is reading all the time. So as soon as we start the state machine, we are in this reading state and in this release state, of course. And during the do, we simply calling this read button function down here. And as we start, we are in the release state. So we know the button is not pressed. As soon as we know that the button is pressed, we want to switch into the pressed state. And when it's pressed for a long time, we switch into the long pressed state. And when it's released, of course, back again from both. So let's do this. We use again the code editor. We have guards and effects, so we can use both in here. In this case, we want to say if the last state is high, coming from Arduino, would be that we have power on it. So when the last state was high, the button is pressed. And when the last me.last state equals low, without this case because it's an if, we want to switch back to released. And of course, the same thing goes for the other side on the long press. And we want to have 2 equals. So you see we have syntax highlighting and stuff like that, but we don't check the code currently. So now that we have this available, we also want to say we want to have the long pressed because we have a, where is it, support long press, and in it it states when the button is pressed for more than 1 second. We simply go to the transition in here. We don't use a guard because we want to have the availability of triggers and signals in here. And again, I have something prefabricated in here. Usually you would enter your triggers in here simply by giving it a name, selecting the type, in this case time, and then we specify it for 1 second. This is a feature of Embedded Engineer that he can read this kind of format. We'll save it. And now we have the basic implementation. What we're still missing is that we want to, of course, send the long pressed and send the pressed information over. And this can be done, not down here because this is not opaque code, but a behavior. So we use effect as a behavior. Use the send pressed action, which we previously defined, activity. Save it and do the same for the long pressed, of course, so we can send the long pressed. And now we have, as soon as the button goes low, the transition will take effect. And as soon as it takes effect, it will call our operation, our activity down here. And the same goes for the send pressed, not only the long pressed. So now that we generate the code, we'll get another error in here. In this case, it's a signal error. We are missing a signal enumerator. We're using signals, and since we want to propagate these signals throughout our code and throughout our application, we need some way of storing them. And this is done with an enumeration. You can call it anything you like. If you call it signals, then it's automatically known to Embedded Engineer that you want to store your signals in there. If you call it anything other than signals, you simply give it a signal stereotype from the Embedded Engineer. does the same thing. And now that we have our signals enumeration where we store our signals and we have everything else, we right click on Embedded Engineer. In this case, we generate the signals and the code. So the signals enum gets updated with the new values. And now that everything is working, we'll get our code out of it without any errors. And we now have 6 files generated. Well, let's switch back to our generated folder. We see our new files, our C and H file. Yeah, these are all changed, of course. And let's take a look at the signal file. Here, as I stated previously, we have our button press and our button long pressed in here, and of course a no signal implementation if no signal was sent to the state machine, or if you want to send no signal to the state machine. On the button side, we have our signals include, we have our enumeration of our states, and we have this FSM structure, FSM states, and a structure for the state machine, another structure for our class containing our attributes and our state machine, because we can have multiple instances of them. Then we have our button read, send pressed, send long pressed, and we have a state machine and a state machine initialize function. Here you see we have this me pointer, which I previously related to. And this me pointer, of course, points to our button struct where we have our currently where we have our attributes stored. This means we can have multiple of these structs and have so-called instances, multiple instances of this class if we want to. And the same goes for our state machine. So we could even have multiple state machines with the same behavior running. And we give it our signals and we're good to go. On the implementation side, we have our button read functionality. You see here the implementation of our requirement. And then you see this is our write variable action. This is our call behavior action. And this is our read variable action. So you see we have 3 actions and I think at least 3 pins or more than 3 pins in there. We're using simply to generate one line of code. Not very effective, but if you want to do it, it's up to you. We have our ifs, which we previously defined. We have our read, our read variable action, our write variable action, and then we have our handwritten code where we have simply entered an opaque action in here. We have our send signal action. The same thing with this state machine and the send signal action is that running the state machine and implementing the signal handling is up to the user, since we are agnostic of the target you're using. So if you want to have interrupts, if you can use threads or whatever you like, you may implement it, and you implement the signal handling and the signal queuing and the running of the state machine on your side, and we simply run the behavior for you. So if you implement this, you get the signal sent, and as long as you run the state machine with the parameters in here, you see we have the read button, which we call. We have the FSM check time, again, such an FSM struct, where we check for 1 second, and then we switch to long pressed, and if we're low, if the last button state is low, we send the pressed state, and if we're in long pressed and we're in state low, then we send the long pressed, of course, and so on. There is the state machine in here. Okay, to make this runnable, to use this inside our code, we of course need this FSM struct. And this FSM struct is also provided with the Embedded Engineer. You simply go to the code package again and go to the model patterns and model wizard. Scroll down to Liebe Embedded Engineer and use the FSM struct, which you can create a pattern from. And then you get this FSM struct containing your FSM state with the current substate and the time, the start time for your timing needs, and of course an enumeration for the time units. And we have an implementation of the check event time, where we check if the time has passed, which was defined inside our time trigger, and we have the get time. And as you see, we have a to-do down here, where it again states, provide an implementation to get the correct time for your target. Would be missing here, but I think you know it already. So you can implement any time you like here, if you use the target time, or if you use some simulation time in here, that's up to you. So all we need to do again is click on generate. And as soon as we have everything generated, oh, sorry, I missed something. Of course, I missed something. We need to add the package here. We can add just to the classes, but there is a feature in Embedded Engineer when we add the package and we create a usage for the package. We link to all the H files in it. So now we can simply generate again because I forgot the package usage. And of course, without any warnings, we see that we have some updated code in here. And when we go to the H file, we see that we have the FSM state, the FSM H, and the signal H was previously here. But okay, so now we have the functionality in here to check our FSM check time and run our code without any errors. So this was a quick and easy presentation on how to implement behavior code in here. So for activity diagrams, we only need an activity diagram and the actions in it. And for the state machine, we also need this additional FSM state structure, which the embedded engineer provides. You don't always need to generate the FSM structure. So if you have it already available inside your source code, you can, of course, use it. But to have the usage in there, you need to link it here. So that's it for the second demo. The next part would be how to do round-trip engineering. And as you already see, round-trip engineering, the myth. Since the day I started generating code and started working on the embedded engineer, I always get the question, what about round-trip engineering? And as far as I know, I haven't found a solution, or nobody I know have found a solution that anybody's happy with. Our approach is a little bit different to this. We go back to the question, do I need to model everything? We don't need to model everything. We can have opaque code and we have something in the model. So we think that the main behavior should always be modeled and the rest can be opaque handwritten code. And this way we bring the architects, the software architects and the software developers together without interfering in each other's work. Because the architect can model the structure and the behavior on a high abstraction level. No need to think about target implementation, low-level driver or registers or something like that. And on the other hand, we have a predefined structured code containing high-level behavioral implementations for the developer. And the developer has, of course, the freedom to implement the target code in his own IDE without the use to open UML modeling tool. Would be crazy to do it this way. But okay. And for this, we have the alternative called code sync. So let's take a look at the code sync. So I'll show you how we implement the code synchronization, how we keep parts from architects and developers apart, and if there are some parts that mixed, how we handle these conflicts in the parts. So for the last time, we go back to Embedded Engineer. In this case, I'll again show you the buttons, the information in here. We have our very low level of abstraction and our pretty strict code in here and our high level of abstraction down here. And when we look at it in the code, again, we have this part is modeled, this part is modeled. And then we have this small part with this syncable user code flag, where it starts and stops. with the syncable user code part contains an GUID linking back to the element from where it came from, and a small hash code hashing the code inside of it. So we exactly know if something in here has changed. So let's start simply by having a developer that say, okay, the debounce is enough, we don't need this in here. Just delete it down here. So now we have changed something that's modeled. Okay. On the other hand, we have this syncable user code in here flagging back to our opaque code, to our opaque action. But not only here, we also have it. We want to take a look here inside our FSM structure, of course. We have a syncable user code in every operation we have in here. So for example, I'm the developer now in my IDE and I see, okay, this is system time, this won't work really properly. So let's change this to millis. Since we're using Arduino, we know that we can choose millis. So we have changed some syncable user code in here, and we have changed some behavioral code, modeled code in here. And now to be extra funny, let's go in here and say, okay, the developer, here we go, sorry. The architect knows about Arduino and say, okay, we don't need this to do stuff. We don't need it anymore because I know we want to have milliseconds. But since we also have another implementation, let's use micros. So we use microseconds on the other hand. So now we have changed it inside the code and also inside the model. And now simply generate the code again. And let's see what happens. Well, we see we get an sync conflict. So we have a warning down here. So if we scroll up, we see sync conflict in operation get time. We even have a code change report. So let's open this code change report. Inside this code change report, we see, okay, somebody has changed something from the model to the code. We have something in here which was deleted inside or is present inside the code, but not present inside the model, and so on. And on the right-hand side, we see inside the model, it looks like this, and inside the code, it looks like this. We can even view it inside the code by just simply inside the model by simply right-clicking, show relevant element model inside the progress dialog. So we're jumping to it and already have it selected on the right-hand side here, and we see somebody needs to resolve this conflict for us. So we can do it on the code side or on the model side, wherever we like. Let's just simply change this, save this, and generate the whole thing again. And of course, what I've missed is our changed behavior. As I said, behavior should be fixed and should be coming from the model. You see, the developer has changed it, but we haven't synced it back because this is defined inside the model and should be only changed by an architect. And on the other hand, during the next generation, it's set back again because it's not inside a syncable user code flag. But when I take a look at our implementation down here, our error was resolved and was set to the new implementation done on the model side. Again, you can do it on the code side and sync it back. It's up to you on which side you do it, what's your favorite side to do it. But we can handle these conflicts, can show these conflicts, and you can, of course, resolve these conflicts. Okay, so what have we learned from this? Even if you don't want to dive in head first, you still can have benefits from modeling or just defining interfaces. You can even extend the reach of your requirements into the code to aid you with your documentation, simply by linking them inside of Enterprise Architect. You don't need to model everything, or you don't need to throw away legacy code. You can reverse engineer it into your model and use it to solely transition from your old workflow to your new workflow with behavioral code. And with the new code editor, with the code documentation, with the custom documentation and the Clang style options, you can customize the code to your needs or to your company's requirements. And I think we have found a way that we interface the architects and the developers, or should I say the models and the code itself. So the only thing left to do is download the Embedded Engineer, take it for a spin. We have a trial version for 30 days. You can use our online help at help.lieberlieber.com for further information. You can contact us for a presentation or for trainings at welcome@lieberlieber.com, or again, as stated in front up, in the MS Teams chat. And if you have any further questions, I'll be happy to help you with an answer. And thank you for your attention. So
then thank you, Richard. It was a very great to have you on the call. I guess many would have got very good inputs from the topic that you've taken. We have a query here, which I mean, is it fine for you to address it here?
If we have still time, then no problem. Yeah, why not?
Yeah, just one query.
Okay.
Mr. Dinesh has asked, can we use any kind of embedded systems such as microcontroller and microprocessor coding to it?
Yes, as I said, the embedded engineer is totally agnostic to the target it runs on. Since we don't have a prerequisite or a system requirement to have threads, to have interrupts or whatever, we are providing you with the modeled and generated behavioral code, and how you implement it is up to you. We have some examples online where we use it on without embedded stuff on simply a Windows form with Visual Studio. And I even broken it down to an 85, where we had an example running on the embedded world, where I see how low and how low level we can go with our implementation. So we are totally agnostic to the systems, to the target system you're running on. All you need to have is a model of it. We generate the code, and you can implement it on your target site without any errors. And as I said again, the UML debugger, which we provide, is simply a debugging tool that allows you to connect to your target debugger. So we are interfacing the debugger you're currently using, and remote controlling is stepping through the model and showing you on the model where your code is currently running on the target.
Okay. Thank you for addressing the query.
No problem.
There are a couple of other queries on the Teams channel.
Yep.
It would be nice if you could take some time out for it, probably after this call.
Of course, I will switch over there shortly.
Okay, great. And thank you all for joining the wonderful session. The video of the session will be made available post the summit, and we'll notify you once everything is available. Thank you all.
Thank you again.
Thanks.
Bye.
Bye.